Okay, this is going to be the answer key for the review sheet. Okay. All right. So what happens to the total energy of a system as you look at multiple state diagrams? Okay. We might even say as time passes, something like this, right? Okay. And what we want you to say is that the total energy of the system, okay, remains constant or stays the same or is conserved. All of these mean the same thing, okay? The total energy does not change from picture to picture, from bar graph to bar graph. Once you have a certain amount of energy in your system, that's it. That's what you've got, okay? All right, for the relationship between the speed and kinetic energy, okay? So when the speed is higher, okay, or the object is faster, the kinetic energy is more or is larger or whatever, something like that, okay? So the higher you are, the more EK you have, all right? So for example, somehow that you might see this, right? So like if I have a car that's just stopped, it would have no EK, all right? If I have a car that's moving, like semi-fast, right, it would have some amount of EK. And if I have a car that's moving very fast, it would have lots of EK, all right? So what we're looking for here is the relationship between the whooshies and the bar graph size, okay? So bigger, longer whooshies, okay, should mean more kinetic energy, okay? So when you're doing your analysis, you have to check that, because that's what I noticed on the quiz, was that a lot of people didn't have that consistency, okay? So see, no whooshies here, no energy. Medium whooshies, medium energy. Long whooshies, lots of kinetic energy, okay? That's what we're looking for, all right? Okay, write a sentence describing the relationship between height and gravitational energy, okay? So the higher above the ground, okay, remember, we don't care about the air, in the air, flying, whatever. The higher above the ground level, okay, the more gravitational energy is stored, okay? Right? So keep in mind, when you have something, like let's say there's a guy going up a hill, right? So maybe like he's here, then he's here, then he's here, all right? And I'm not even going to put the whooshies because I don't even care. It doesn't matter if he's moving, if he's up and down, if he's whatever, all right? You need to make sure you know where your ground level is, all right? So remember, the ground doesn't mean the surface you're standing on. The ground is like a level, like sea level would be the ground level, or whatever you choose, okay? So I might go ahead and mark the EG equals 0 level in my picture, all right? So this first guy is slightly above the ground, okay? So he might get, say, 1 bar. Maybe this guy here is higher above the ground, so he would get 3 bars. And then this guy is really high, so maybe he would get 5 bars, all right? This is not dependent upon anything else that's happening. He's moving, he's fast, he's slow, he's purple, he's going backwards, he's flying, he's in a car, he's in a kite, like whatever. None of that is relevant. All I'm looking at is how far off the ground he is, okay? Right? Depending on the situation, if the ground level's not given, I could have said like maybe this level is the ground, okay? And I could say that, right? It doesn't have to be like the very bottom of the picture. It could be the lowest point that the thing is at, all right? That's also a way you could do it. Your call, unless it's set up a certain way in the problem, okay? And if that's the case, then you better make sure you mark that, okay? If it doesn't look like the very, very bottom, okay? All right, relationship between stretch, compression, and elastic energy, okay? So the more an object is stretched or compressed, okay? And we're probably going to focus on things that are one or the other, all right? Not like the mass on spring. That one's kind of confusing because it does both, okay? But it'll probably be either like a rubber band or a bungee cord stretching or a trampoline stretching or a spring compressed that's going to fire like a dart or a car or something, okay? So the more an object is stretched or compressed, the more elastic energy is stored, okay? All right, so for example, if we were looking at, say, like, I don't know, a bungee cord or something, right? Maybe like when the guy is falling and the bungee cord is slack, then it'd be nothing, okay, because there's no energy stored because that cord is not stretched. And then maybe in some middle position, you know, like it's partially stretched, then it would have like some EE, or maybe it's like really stretched, really tight, okay, then it might store a lot of EE. Okay, so it's all based on the amount of stretch and compression, all right? In a spring, right, maybe like if a spring is super coiled up, right, it would store like a lot of EE, right? And then like if it's a little more unwound, maybe a little less, and then eventually like it's all the way unwound, like if it's firing something, then it would be nothing, okay? All right, so that's based on the amount of stretch and compression. And again, you got to check that in your pictures. You have to check to make sure that it looks like what's happening in the pictures. All right, okay. The last one is how thermal energy changes when friction is present. Okay, so when there's friction, that rubbing is going to generate thermal energy. Okay, so when there is friction present, okay, thermal energy is generated, okay? Let me not say generated, is stored. I don't like the word generated, okay? All right, more of that transfers to the thermal column. More of the available energy transfers to the thermal column, okay? So like if you have like a track of some sort, okay, right? When the thing starts, no matter where it starts, there's no E thermal, okay? We don't even include it in the first picture. That's like your baseline, okay, for how hot it is, sort of, okay? Right? So then if this little, you know, I don't know, marble's running along this track, and maybe it gets to here, it's had all this track to rub against, so it's going to it's going to transfer some of that energy to thermal energy, okay? And then by the time maybe it gets to over here, right, it had that much more time to transfer more into thermal, so that bar is going to continue to grow. Okay, so the more time that it rubs, then the more energy will be stored as thermal. Okay, this can never decrease. This can never go down, okay? Once it moves into the thermal column, the energy, it has to stay there. It can't go back. That's the whole thing with thermal energy. That's energy that's sort of wasted. It's unusable. You can't transfer it back to another column to make something else happen, okay? Eventually, that process will end, and that thermal will take over all the energy, okay, depending on the process, okay? We probably will focus on the test more on thermal like this than on like things that, you know, might generate thermal energy in like an impact or a crash or something like that. Okay, I think it's more likely on the test to be something like this where the thermal is going to continue to grow as the thing keeps rubbing along the surface. Okay, all right, so that's the basics. So I would expect, again, I don't know what the test looks like exactly yet, but I would expect one page of the test to be something like making sure you understand these relationships individually at their most basic levels, okay? Total energy, and then the 4 different energy storage modes, what their relationships are, what make them to have more or less energy in that column.